Mendeleev really originally organized the periodic table, and his periodic table originally looked like this. Okay, it's a really blurry picture because I'm sure this is the original. You know what I'm saying?
Yeah.
Yeah. Okay, so this is how we organized the periodic table. This dude was so smart, he even left gaps in the periodic table for elements he knew were going to be discovered. Okay, but he hadn't discovered them yet, or they hadn't been discovered yet, but he was so smart, he was able to figure out the patterns in the periodic table, and he left blank spots about where they think they're going to fit in. So here is how he arranged it to begin with. His arrangement, okay, maybe you want to write this down, but Mendeleev's arrangement is first by atomic mass, not by atomic number. Okay, he organized it by atomic mass. So his name's Mendeleev. He organized his table.
Did he not even name like any of the elements after him?
There's Mendelevium.
Where's that?
But I don't actually think he named it. I think someone named it after him. So he organized his periodic table by atomic mass. Eventually, a new guy came along named Henry Moseley. He started organizing it by atomic number, which is how it's organized today. So if you follow atomic number, that's the whole number. Does anyone remember what's the atomic number represent? What does it tell us? Not how many atoms, how many protons. How many protons it has. So if I'm looking at potassium right here, how many protons does potassium have? 19. Very good. So that's how the periodic table is now organized. Okay, so today it is organized by atomic number. Okay, so I'm going to make a little extra note here. Today we organize it by atomic number. Okay, the way it's organized and the way it's laid out today gives us a lot of patterns. It shows us a lot of patterns. It shows us valence electron patterns. It even like elements that are near each other on the periodic table, they behave similarly, right? Not exactly the same, but they behave similarly. They have a lot of the same characteristics in terms of melting point, boiling point, all that kind of stuff. So the way the periodic table is organized is it's pretty crazy, right? Because it tells us a lot of information about an element just because of its spot on the periodic table. So if I look at fluorine, for example, okay, if I look at fluorine, F number 9, do you see that on your periodic table? Why don't you grab yours out if you don't have it already, okay? Fluorine is over here, it's number 9. By the fact that it's in this group right here, up and down, group 7 or 17, it tells me it has 7 valence electrons. Okay, just from that, I know based on where it's placed and where it goes, how far down on the periodic table it is, I know that it's extremely reactive. I know that it wants to bond with anything and everything, right? All of this information you are going to be able to gather from the periodic table as we work through. Okay, so it tells us a lot of different things. All right, the next thing I want to kind of hit on with the periodic table is that how it's organized. Okay, we kind of talked about similarities, but I want us to look now at specifics of how it's organized. It is organized into groups and periods. Did the video talk about that? Groups and periods. So which one goes up and down? Groups. Groups are the columns. Groups are the columns of the periodic table. Sometimes they're called families. It might say I don't ever call them that. Your book sometimes every once in a while, but again, we don't use our books that often. So you will hear me call them groups, okay? They are organized vertically in what's called groups. That is by far how we reference the periodic table is group 1, group 2, group whatever. So I want you to take your periodic table right now, and I want you to see on the top, I want you to label each of them. Okay, I want you to label them with a group number. Okay, and so what that means is, okay, so within a group, we would expect those elements to behave similarly, okay? Now we're going to look at what goes across a row. That's called a period, okay? And these elements kind of change behaviors as they go down the row, all right? They change behaviors as they go down the row. I'm not going to have you label the rows because we very rarely refer to elements in their row, okay? But I want you to look at this third row right here. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. That third group. third row. I shouldn't even say group. Okay, the third row, or that third period. Sodium and magnesium behave somewhat similarly, but then as you start working across, you get to sulfur, you get to chlorine, you get to argon. All of those elements become now no longer solids at room temperature. So they behave very differently as you change down the row, okay? But like we said before, elements that are close together on the periodic table tend to behave alike, or similarly at least, okay? The one thing I would like for you to make sure you define on your periodic table is this black zigzag line that goes right here. Okay, you see that black zigzag line, or that, now I'm making it blue? You see that right there? I'm making it a different color. What color can I make it? Maybe green? You see this zigzag line I made right here? This is something I want you to draw on your periodic table, okay? This gives us a defined split between metals and nonmetals. A couple things I want to point out here about the periodic table. What types of elements make up a majority of our elements? Metals, nonmetals, or metalloids? Metals. Metals, by far, right? Metals are the red ones. They take up a majority of our periodic table. So when I talk about the periodic table, I will use this line, this green line right here, which I call the stair step. That will be used as a point of reference a lot. I'll say to the left of the stair step, right? That still includes a lot of the periodic table. Okay? So when we say metals are on the left side, we mean of the stair step. Okay? So metals are all these reds right here. Hydrogen sits on the wrong side of the periodic table because of its valence electrons, and we'll talk about that here in just a second. All right, if we go looking at group names and group characteristics, in your video you talked about group 1 being the alkali metals, right? We talked about all those different things in the video. So I want to just show a couple things here with group 1, okay? Group 1, I don't care about its experience or whatever, but group 1. We need to know that group 1 elements, all of the elements in group 1 have one valence electron. Okay, you're going to see me abbreviate it like that. One valence electron. Actually, I like to abbreviate it like this. One valence electron. Okay, all the elements in group 1 have one valence electron. Let's talk about this right here first so we know what that means. Valence electron. That's the abbreviation for that. You're going to see me use it a lot. Okay? Okay, what do you think? Why do you think there's a line? Why do you think there's an E with a little minus sign? Electrons have a negative charge. That's why. Very good. So when I abbreviate E with a little negative, that means electrons. If I'm talking about protons, I'll do it like this. P with a little plus, right? Because protons have a positive charge. Does that make sense why I do that? I need to write them down every time. Yeah.
Wait, the blue one's called,
Alkali metals. But that's not the blue ones on this previous. If I'm looking here, the blues are just called non-metals. Those are non-metals. Okay. So back to group 1. Group 1 elements have one valence electron. That's why hydrogen sits there, because hydrogen only has one valence electron. Hydrogen is not an alkali metal because it's not a metal. Okay? It does its own thing. So group 1 has one valence electron. We're going to see that pattern a lot. There is something that's interesting about group 1 being extremely reactive. So I want us to watch this little video here about the reactivity of group 1 metals because it's kind of interesting. Okay? That one valence electron makes it extremely reactive. And I'm going to tell you why in just a second. No, not. Oh, goodness gracious. I clicked on the wrong one. There we go. All right, so we're going to look at alkali metals reacting with water here.
start with lithium. The metal floats on the water and reacts with it, giving off hydrogen gas.
Can we put it back in the...
Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous. All the alkali metals react with water in the same way. Now for potassium.
Okay, so do you see he's working his way down the group 1 metals. Lithium was reactive. Sodium became a little bit more reactive. Now he's looking at potassium, which is K. Okay, do you see how he's working his way down group 1?
The flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time, we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our fifth alkali metal.
Okay, so they become a lot more reactive the farther they get down the periodic table. Yeah. Yeah, they didn't even do francium. That would be too dangerous. Even though like sodium, lithium, they're not super reactive, if you would hold sodium in your hand, it would burn your hand because just the water from your skin and from your body would cause that to be reactive. It would burn, right? Maybe not right away, but I know like if people, I've heard a story of someone that had it in their pocket for some reason and ended up burning a hole in their pocket, burned their leg just from that amount of water. So it does get kind of reactive. Let's talk about why that's so reactive. One valence electron makes it reactive. Does anyone know how many electrons that atoms want to have? 2 and then 8, right? First shell gets 2. Otherwise, they want 8 electrons. So let's think about sodium, for example. Sodium has 11 electrons. It looks like this. Sodium, it has 2 electrons. Then it has 8 in its shells. Then it has 1 in its outermost shell. Is it going to be easier for sodium to give away that 1 electron or to gather in 7 more? Give it away, right? So sodium will give away that electron to anything and everything and bond with that thing. And so that's what makes it so reactive. It will bond with anything and everything. So that valence electron makes a big difference. Okay, I'm not going to go through the rest of the groups here in a lot of detail, but we need to understand that now, following that same pattern, group 2, called the alkaline earth metals, has how many valence electrons do you think? Group 2 has 2 valence electrons. So we're going to see that pattern come up over and over and over again. Group 1, all of those elements have 1. Group 2, all of those elements have 2 valence electrons. Okay? They have 2 valence electrons. They are pretty reactive as well because it's easier for them to give up 2 than to bring in 6, right? There are 18 in total, but we don't count the 10 in the middle, right? So we go to 8. That's okay. It's okay. 18 total, but the ones in the middle, we don't exactly count those. Okay. Oops, I'm going to skip over all that part. Here are the groups that fall in the middle that we didn't really name or didn't really give a group number. They are called the transition metals. The transition metals, okay? Those are the groups that are on our periodic table in the classroom. Those are the red. Okay, so look at our periodic table up here. That group of dark red, rust color, those are called the transition metals. They don't follow the rules, and we didn't actually assign them a group number, okay, but technically they're 3 through 12, right? Then we pick up again at 13.
So it's just something that like you do or do
so there's 2 different ways that you can organize the periodic table. When we just use the 1 through 8 method, like I like, they're called 1A, 2A, 3A, 4A. So there's 2 different ways you can name it. Some periodic tables will have them both listed up here on the top. I just chose a blank one. Okay, so that's two valid methods. It's just kind of pick and choose. Yeah. We very rarely refer to the groups in the middle like these transition metals. Okay? You'll notice in the transition metals are a lot of the metals that we traditionally think of as metals. Okay? In there is silver, gold, copper, mercury, titanium, zirconium. A lot of things that we are used to as being metals are found in that transition metal area. Okay? I'm going to skip over to group 7 or 17 called the halogens. Okay, the halogens are group 7 or 17 if you're naming them that way. How many valence electrons do you think that group has? They have 7. 7. Remember, we're going to just label them 1 through 8. So these guys have 7. Let's call it group 7. They have 7 valence electrons. Okay? So if you had to take a guess, would you say that elements in this group are pretty reactive or not very reactive?
Not really reactive.
Okay, here's the thing. They are really reactive because how many electrons do they need to fill their octet? They want 8, but they have 7, so how many they only need? 1 more. So they will bond with anything and everything to take that other electron. So the halogens are really reactive. Okay?
Do the transition metals have valence electrons?
Good question. So I skipped over that part. Ty asked, do the transition metals have a certain number of valence electrons? The answer is no. They don't follow the rules, which is why I left them out of that count, 1 through 8. Okay, very good question. The last group I want to talk about today is the noble gases. Those are group 8 or 18. Okay, so we'll call it group 8. Oops, sorry. The noble gases are group 8 or 18. How many valence electrons do you think they might have? They have 8 valence electrons, which is how many they would like, right? They have 8 valence electrons. So do you think they bond? Yeah, very good. Do you think they bond with anything?
No.
Not so much, right? They are perfectly content being by themselves. Okay? Fun fact is that all of the noble gases, helium, neon, argon, krypton, xenon, radon, those are all gases involved in making neon lights, right? We call them neon lights, but those and the mixtures that they have give us different colors of neon lights. So that's kind of the difference there, right? But it's kind of fun fact. Okay? So how do we feel about kind of our introduction to the periodic table? Do we see some patterns, see some things we're picking up?
Yeah.
Okay, so I want you to look at your periodic table, and I want to answer a couple questions here. If you are looking at your periodic table, and I asked you, how many valence electrons does silicon have? How many valence electrons does silicon have? Raise your hand if you think you know.
Wait, which one's silicon?
Silicon is Si. It's number 14. How many valence electrons do you think it has?
4.
It's number 14. Raise your hand, see if you think you know. All right, Nora, what do you think? How many? 4. I would agree. It's in carbon's group that we're going to call group number 4. That means it has 4 valence electrons. So tell me, based on what you know about reactivity, do you think silicon's very reactive or not? What do you think?
Actually, yeah. 1. Yeah.
It's in the middle, right? It's got 4 valence electrons. So it doesn't want to give away 4 or gain 4. You don't know, right? It kind of does both things, right? It can act as both a cation and an anion, which we'll get to later. But yeah, their reactivity levels are nothing in comparison to the outsides of the periodic table. Okay, group 7, group 1 and 2. Okay? If I asked you how many valence electrons does calcium have? Locate calcium and tell me how many valence electrons it has. How many? Say it out loud all together. How many? 2. Very good. It's in group 2, so we've got 2 valence electrons. Do we feel okay about identifying group numbers?
Yeah.
Very good. Okay. Last little part of the periodic table here are the lanthanides and the actinides. Did it hit on that in the video? Lanthanides and the actinides. Where do they sit? The very bottom. Lanthanides and actinides. Okay, now on your periodic table, oddly enough, lanthanum and actinium are in the periodic table itself. In ours in the classroom, lanthanum and actinium are down here, okay? Sometimes they get stuck up here and sometimes they don't, but that's why they're called lanthanides and the actinides. They start with those 2 elements, and they fit right in here. It would expand the periodic table and make it honestly pretty ugly if we kept it like that, but that's where they fit, right? 57 through 70 fits in this little spot right here, and the 89 through 102 fits right in there. So that's why that gets pulled down, okay? Because if we didn't, it would look like that. If we didn't, our periodic table would look like that. Okay, so it would not be as aesthetically pleasing, okay, if you will. Okay? So let's talk about a couple other things. The lanthanides behave similarly to the group 2 elements. So lanthanum, cerium, all of those down there, they're going to behave similarly to the group 2 elements. Give me an element that's in group 2. What's one element that's in group 2? Magnesium, beryllium, calcium, all these guys right here. Okay, those are all group 2 elements. Okay, the actinides, on the other hand, are all radioactive, and only some of them are found naturally on Earth. Some of them are man-made. Okay, when we say man-made, we mean in a lab. Usually they're man-made with very little stability, right? They might only exist for a small fraction of time, and then they kind of dissipate, right? Or they rearrange. Tell me, how many elements do you think are man-made? How many? Take a guess. There are 35 man-made elements. Okay, so write that down. Maybe highlight it. Like maybe it's going to be a test question. Okay, 35 man-made elements. They're kind of all over the board. Honestly, if you find elements that sound like they're made up, that means they're probably man-made, right? If you see elements like Californium, Americium, I don't even know how you say that, okay? And Einsteinium, probably those are man-made elements, okay? But anyway, 35. Eum has to do with the Latin version of their regular name, right? This is how it comes through. So all of them are named originally in Latin and then now have been translated. But there are 35 man-made elements.